Hi there, folk. We're busy looking at this section on graphs. And as a way of introducing this section, I want to tell you something I was thinking about the other day in a little experiment I did and calculated. I was looking at the moon the one night. And if you look here, you can see that we're on the Earth over here, and over there is our moon. And the distance between Earth and the moon is 384,400 kilometers. That's quite a distance. To put it in perspective, if I took this distance of 384,400 kilometers, and I said, well, the distance between Joburg and Durban is round about 600. It's just less than 600, but let's work on 600 kilometers, okay? If I divided that by 600, I would get this phenomenal answer of 640,66. Let's say 641 times. In other words, if I got in my car and I drove from Durban to Johannesburg, or Johannesburg to Durban, I would have to do that trip 641 times in order to reach the moon. Sure, that's a lot of traveling, okay? That's how far the moon is. And it's amazing we can actually see the moon when you think of that's how far away it is, okay? The moon must be pretty big, and the Earth must be pretty big, okay? So, a distance of 384,400 kilometers away. Now, if I took a piece of paper, let's say a cardboard, and the cardboard was 1 millimeter thick, okay? Pretty thick cardboard, 1 millimeter thick. And let's say I folded that cardboard in half. And I would then have a piece of cardboard 2 millimeters thick. Would you agree on that? And if I took that folded cardboard and I folded it again, I have 2, folded again, I've now got a piece 4 millimeters thick, right? If I fold it in half again, I would have a cardboard piece 8 millimeters thick. Cool. So what I thought of was this: if we could take a piece of paper and fold it 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 and fold it. Now I know you can only take a piece of paper and fold it about 7 or 8 times and then you can't fold it in half again. But let's just pretend we could always fold a piece of paper. We've got a big piece of paper and we kept folding, kept folding, kept folding, kept folding. How many times would I need to take that piece of paper and fold it in order to reach the moon? Okay. Now, this is what we do. We take a 1 millimeter, and I'm going to change that to kilometers straight away. And we'll learn how to do that in one of our next sessions. But 1 millimeter is equivalent to 0,000,001 kilometer. Just believe me, for now it's true. Okay? So I double it, and I'm obviously then going to land up with 0,000,002 kilometers. Double it, 0,000,004 kilometers. Double it, 0,000,008 kilometers. And we could keep going on like this for another 20 minutes, and that would be the end of this session, but I'm not going to do that. But if I kept doubling and kept doubling and kept doubling, how many times would I have to fold a piece of paper in order to reach the moon? Give it some thought, okay? Now, I know some of you are thinking, yeah, it's like millions of times, bro, okay, to reach that moon. And some of you are saying, well, it wouldn't quite be millions, maybe a few thousand times to reach the moon, okay? Then the odd person's going to say, right, 100 times. You're going to think, oh, 100 times, you're totally crazy. I'm going to write the answer down on the screen, okay? When I fold a piece of paper this amount of times, I would have passed the moon. Watch carefully. 3, 9, and that's all. 39 times. That's unbelievable. And I know you're sitting there thinking, never, bro, that's impossible. But it's true. You take this number and keep doubling, keep doubling, keep doubling, keep doubling, and do that 39 times. Okay? Take your calculator. Say 0.000001 times 2, times 2, times 2. And times 2 39 times. You will get a number bigger than 384,400 kilometers. That boggles the brain. As you say at school, deep. Okay, this is deep stuff. And it's all to do with this whole wonderful concept of exponential power, okay, of just increasing something, and it suddenly gets bigger and bigger and bigger and bigger and bigger and bigger and bigger, and that's what we're going to look at now. Graphs with drawing graphs with exponential power. I want us to have a look at this example. Now it gets interesting. Okay, exponential number patterns and graphs. Sometimes a graph will show an exponential growth. Exponential growth is a situation where the graph first increases slowly and then increases quickly. This is different from a straight line graph, which shows a constant growth. So let's have a look at these two different scenarios. A farmer starts with 20 fruit trees and plants 20 more fruit trees every year. The rate of change is the same each year. What's the rate of change? The rate of change is 20. So year 1, he plants 20 trees. Cool. Year 2, he plants another 20. How many he got? 40 trees, right? The next year, another 20, 60 trees. The next year, another 20, 80 trees. What do you notice is the difference here every time? Every time there's a difference of 20. 60 minus 40, 20. 80 minus 60, 20. 100 minus 80, 20. 120 minus 100, 20. Why is there a difference of 20? Because every year he's planting 20 trees, 20 trees, 20 trees. So the growth is constant at 20. Okay, do you understand that? Now let's look at another scenario. Another scenario is this. A farmer starts with 10 sheep. Each sheep produces another lamb every year. The number of sheep doubles every year. The number of sheep is dependent variable. Okay, so we start off, we begin farming, and we got 10 sheep. In our first year, every one of those sheep have a little lamb. Okay, so we'd like to believe that our 10 sheep are all female sheep because they're all having lambs. Okay, that's a biology lesson. Right, so now, at the end of year 1, we got 20 sheep. So we started with 10, we now got 20. Those 20, every next year, each have a little lamb. So we start with 20, each one has a lamb, means we've got another 20. So at the end of year 2, we now got 40 sheep running around on our farm. Now, each of those 40, and it's a miracle, this whole thing, okay? Because every time they give birth to a female sheep, okay? Because every year they're reproducing. So no males are ever born here. We only get females, okay? It's just a wacko scenario, but we're going to go with it, okay? Those 40, each of those 40 have a little lamb. The end of year 3, we now have 80 sheep because we had 40 and each one had a little baby. Now, following year, all those 80 have a little lamb. We now got 160, and the following year they have a lamb. We now got 320 sheep running around in our farm. Now, this is what I want to point out to you, and I'm going to use a different color here. My difference here is 10. My difference here, 20. My difference here, 40. My difference here, 80. My difference here, 160. So there's an increasing rate of growth. Whereas with our trees, there was a constant rate of growth. It was going up every year. We had another 20 trees. Here with our sheep, they're producing left, right, and center here. Oh my goodness, we're going to take over the whole land with sheep here because they just keep having more and more babies. And so our number of sheep are increasing and not at a constant rate, but they're like, woo, going ballistic here. Okay? Suddenly we got wacko sheep. Now when we plot that on a graph, let's have a look what happens. Okay? Let's look at this. Here we got number of fruit trees and the time in years. Okay? We started off with 20 trees. Next year we bought another 20. The next year we bought another 20. and another 20, and another 20, and another 20. So my graph is going up. We all agree with that. It's got to go up. Okay? Why does it have to go up? It's got to go up because we're adding to the trees. And my graph is showing an increase. It's also showing a straight line, which means it's a constant increase. It's not changing. 1 year we didn't buy 10, then 20, then 40, then 50. We're buying 20 every year. So that's why I have a straight line. Okay. The only thing with this graph, would you say we're correct in drawing a solid line, or should it have been a dotted line? I would say it should have been a dotted line, because I don't have 1.5 trees and 2 1/3 of a tree. I got 1 tree, then 2 trees, then 3 trees. Okay. Now, let's have a look at our little sheep. Right. Vertical axis, the number of sheep that we have. Our horizontal axis, the time in years. We started off with 10 sheep. Then we had another 10, so we had 20. The difference was 10. Each of those 20 had another 20, and so we shot up to 40. Each of those 40 had another 40, we shot up to 80. Each of those 80 had another 80, we shot up to 160. Oh my goodness, we've gone off the graph. We stop at 120 and the 160 is going to be up here somewhere. My graph's going to go like that. Now look what's happening. My graph is increasing, absolutely, but it's not increasing at a constant rate. And the reason I know that, I don't have a straight line. My graph is going up in an exponential kind of graph. In other words, it starts off going slowly and then it goes crazy, 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 going higher and higher and higher and higher and higher. Okay. It's the same thing that's happening at Hartbeespoort Dam at the moment. Okay. All that hyacinth, that weed that's going on in the dam, they say it doubles every day or doubles every week. Okay, so if I've got a little bit of plant and it starts doubling, it's going to double. Then the next day it's doubling. So we got 1 bit of plant. Next day we got 2 bits. The next day we got 4 bits. The next day we got 8 bits. Then we got 16 bits. Then we got 30. And that's why the municipality at Hartbeespoort have got to sort out that whole problem with the hyacinth, with their weed on their dam, because it's just developing and growing and growing and growing at an exponential rate. So you cannot say with a graph like this that on day 2 I had 20 sheep, so on day 4 I'm going to have 40 sheep because I'm increasing by 10 every day. I'm not. I'm doubling. And so my growth is suddenly going crazy. And that's why that whole idea with the moon and the earth, if we take a piece of paper, fold it over, we're only increasing it by 1 millimeter. But when we got paper this thick and we double it, it's now not increasing by 1 millimeter, but it's increasing by that amount. If I got a piece of paper and I folded it so many times and it's now a kilometer high, okay, a kilometer is like way up, okay, it's 1,000 meters up, and I double that, it's now suddenly increasing by 1,000 meters, not by 1 little millimeter. So it starts off with slow growth, and then it gets bigger and bigger and bigger and bigger and bigger. Okay? You take a piece of bread. Do this at home. Do it as an experiment. Take a piece of bread. Put it on your shelf and leave it. Okay? Just leave it. See what happens. After day 1, you'll look at it. You'll take a bite. You'll say, not bad. After day 2, you'll take a bite. Oh, it's a little bit harder. It's okay. After day 3, not the best tasting bread, but we can survive. After day 4, Jesus really does. After a while, it's going to have a little green speck on it. And you're going to say, hey, there's green muck on my bread here. The very next day, there's not going to be one. It's going to be suddenly, whoa, there's so much more green. And the next day, look at all this green. And soon that whole bread's going to be covered with green moss. Okay? Or not moss, green, fungus. Okay? Green yuck stuff. And it suddenly grows. It grows exponentially. Okay? So, let's look here. When we looked at our trees, it is a straight line graph, whereas a compound growth or exponential graph is not a straight line. It's linear number pattern. In other words, there's a difference of the same amount every day or every year with our trees. Here, look at how the differences in the number of sheep increases every year. The first year there was a difference of 10. The next year a difference of 20. The following year a difference of 40. And the constant difference is 20, whereas here the constant ratio is 2. Ratio means it's doubling. Okay. Now doubling is only one example of compound growth. A common example of compound growth is when someone saves an amount of money and earns compound interest on the savings. Okay. So later on, in a later series, we're going to look at simple interest and compound interest. And you're going to realize the power behind putting money into a bank that offers you compound interest, because your interest slowly goes up. You get a little bit of interest, and then eventually you're getting more and more and more and more and more interest, and your money is growing, and wow, life is going so well. But it also has a bad thing, because if you borrow money, that also has a horrible effect. Okay, let's have a look at this question here, and it's to do with money growing in a compound interest account. Tembi invests 1,000 Rand at compound interest. The interest is added every year 10% of the money she has in the account. Fill in the table to show how the money grows. So we start off with 1,000 Rand. The end of that year, we're getting 10% on our money. And 10% of 1,000 is 100 Rand. So we land up then with 1,100 Rand. We then take that and we calculate 10%, not on the 1,000, but on the 1,100. And we land up with 110 Rand. Add that to the 1,100 and we've got 1,210. The next year, 1,331. Now I want to show you the difference here is 100 Rand. The difference here now becomes 110 Rand. The difference here now becomes 121 Rand. The difference here is getting bigger. The difference here is getting bigger and bigger and bigger and bigger. So the longer I leave money in the bank, the more it's going to grow and grow and grow and grow and grow and grow. Exciting stuff. Now, when we put this in our graph, and we plot this in our graph, this is what happens. We started with 1,000 Rand, okay, and that's why it's touching the axis, because even though no time has gone, I've put 1,000 Rand in the bank. And then my money begins to increase, 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 increase. And if I were to carry on drawing this line, it's going to start doing that. Can you notice? It's not a straight line. It's a curved line, and it starts off on a relatively shallow curve, and then the curve gets stronger and stronger and stronger and stronger. Okay, that is exponential growth. All right, now let's have a look at what we've covered so far, and then there are a few graphs I want to show you. So summary. In this segment, we've covered the following. We've looked at exponential growth and graphs. We also need to conclude this session by summarizing the types of graphs that we've had a look at thus far in the series that we've done. And let's have a look at these graphs. So, firstly, we've looked at graphs that are straight line graphs. Okay, so here's a straight line graph. It's not necessarily in proportion because it don't start at 0, 0. But you can see this graph. It's a positive graph. Okay, it's going up, and it's going up pretty steeply, but it starts at 1. Okay, they're straight line, and it can be increasing or decreasing. So this is also a straight line graph, not quite in proportion because we're not cutting at 0, 0. Okay. Then we can have, if an increasing straight line graph starts at 0, 0, it shows a direct proportion. As that goes up, this goes up by the same amount. That goes up, that goes up. Okay? It's a straight line, it's always increasing, and both quantities increase in the same proportion. We clear on that? The other graphs we've looked at is an inverse proportion. It's a curve. It does not touch either of the axes. It's not going to touch my vertical axis, and it's not going to touch my horizontal axis. As one quantity increases, the other one decreases. And then the final graph we've looked at is an exponential graph of growth. It's a curve. It's an increasing graph. It does touch the vertical axis. Okay? Whereas the inverse proportion, we said, doesn't touch. Here, exponential graph has got to start somewhere. It does start at 0. Okay? So it does touch the vertical axis. And the vertical quantity increases more and more and more and more quickly. And that's why we suddenly start with a very shallow curve, but by the time we get here, we get a very steep curve. Guys, this section on graph work is fantastic. It's so interesting, it's exciting, but it's so vitally important. And it's important because every one of your topics could involve graph, especially the topic on finance. And finance is a section that we'll be doing shortly in one of our next sessions. Folks, trust this has been great. Hope you've learned about graphs, and we will chat soon. Cheers.